Right, okay, so I often refer about static tests. I don't usually film static tests, but I thought, well, might be an idea to show you what the kind of tests I do. A static test is something where you basically simulate something and you time it and check the differences. Now it's very, it's not precise science but basically I can only spin this thing by hand at a maximum speed. It's how fast my hand moves basically. So what I usually do is when I'm checking coils, I've actually got, at the moment, I've got two rectangular coils underneath here at the moment, as you can see, and I've got my toroid and a ball bearing in the centre. I don't think you can see that. Right, so I've got two coils side by side, and a toroid and a ball bearing. I'm using the ball bearing simply because that's what I'm testing right now. So, just trying to get this lined up properly again, I've knocked it now. So, stopwatch. I've got the stopwatch on my phone. So, what I'm doing now is, at the moment, is I'm timing it without a load, with just voltage reading, and then I compare with it set on current, and I time it a second time to see how quickly the drum slows down. And by comparing it and by choosing different couplings underneath, I can determine the optimum minimum drag. The reason I'm showing this is because other people might be able to learn about this, how you can do this, and there's a methodology to doing it. Right, so basically what I usually do is I start the timer going. So let's just do it. I start the timer going first, because once I get this going, I've got a process of, I've got to hold this thing basically. So start the timer, get this thing spinning, and hopefully it's not rubbing on anything, which it is at the moment. Oh no, it's just a ball bearing. So we're timing at the moment. Ball bearing is dancing around a bit, and that's the current, that's the voltage. It's only a small voltage, but it's enough for the test. Right, 37 seconds on the voltage setting, without any current load on it, and it as you can see, it ran for 37.87 seconds. Now I'm going to reset. I've made a little bracket to hold my phone, which is just a piece of steel, so I could hold it upright. Right, now I'm going to do it again. I'm going to start the timer, but this time I'm going to switch this meter to current once it's running. So just make sure there's nothing rubbing on me. Oh, my ball bearing. Go back in there. Right, everything looks okay. Right, start the stopwatch. Current. We're on current now. 33 milliamps and dropping. 27 seconds. Right, so we basically lost 10 seconds by having a load on it. That's not bad really. It didn't come to a complete halt, and we were using about, 40, 50 milliamps to begin with. Obviously it was dropping as it was slowing down. So that's the test with the ferrite ring and the ball bearing. Let's take the ball bearing out. Let's do this again. Let's just reset. Put this on voltage. Let's start the timer. Oops. Right, 35 seconds. Without the ball bearing, it actually ran less. It actually ran slower. So 35 seconds without the ball bearing, but that could have been me. I might not split it as fast. There's margins for error with this test anyway. Reset. Now without the ball bearing, I'm going to start it again. I'm going to switch to current once it's running. Start. The current. Huh. 27 seconds, 0.71. That was just without the ball bearing. So does the ball bearing make any difference? I can't remember what it was before now. It certainly made some difference. I can feel it on the vibration on this end. I'll stick the ball bearing back in again. Let's try that again. Put it back on voltage. Reset. Right, start. My hand's catching the rotor a bit, which is annoying. Right, 26.19 with the ball bearing. It would have been 27, but my hand touched the edge of there a little bit when it was going. Let's just repeat that one again. Come on. Well, 29 seconds with the ball bearing and the power ring. So, yeah, I might have gone a bit faster than that time, I don't know. But anyway, the point is, this is how you determine different things. Now, if I cross-wire the coils, that is, the coils are wired so that when the particular pole is directly above both coils equally, they will effectively produce no voltage at all, because I'm going to cross-connect them so that the only way that these two coils will produce power is basically in series, and they are in series at the moment, but they're in series in such a way that the computer's going to sleep. They're in series in such a way at the moment, whereas both coils, if they receive the same pole, they're producing power. Now, if I change the wiring so that when the north magnet is over this coil and the south magnet is over the other coil, that's when they're going to produce output. That's when the magnets are actually perpendicular or north-south, and then the coils will produce power. So I'll change the wiring on this jumper, and so that we produce power in the gaps between the north and south magnets. So it's going to behave differently now. So ball bearings just come out. Right, so let's put on voltage. Phone's going to sleep. Flipping thing. Reset. Right, 1 voltage. I'm going to do a test on voltage first. Start. And the output is a lot lower. I hope I'm connected. Why is it like that? Right, 35 seconds without any load, with just voltage measurement. 35 seconds with these 2 coils wired in this configuration. So, reset. Now let's do the same thing again, but I'm going to switch to current once it's running. Right, so start. That went up to around 40 milliamps. Right, 33 seconds in that configuration. But the output was lower anyway. There was a lower output, but it did seem to go. It did go longer than it did on the other configuration. Now, if I swap the jumper back to where it was, and put that one on the red, put that one on there. See, what I'm looking at is the seesaw effect. So that when this pole here and this pole here is across these 2 coils, that's when they produce power. And we get a very interesting, actually, looking at this under a magnetic film, it's fascinating. Let me just get my magnetic film actually and see if I can show you it. I'm going to step on my wires. It has got a very strong output field on it, and this drum. So right, I don't know if you can see that very well, but that is the magnetic field of the drum. I'll just turn it to an angle so I can hold it properly and turn it. So there's the field of 1 pole. You can see the divider line there as I turn this. So that's the field of it, and it does extend out quite a long way. If I go to the edge, let's just take it off the stand a minute. You can see the lines. You get light reflecting on it. You can see the lines. The field extends a long, long way. Just rotate. It comes way out here, way out here. Oops, too high. Just look at that. Look at the distance of that field coming out. That's when you've got magnets of the same polarization, 3 groups, all the same polarity, all side by side. You can get a much larger extension of the magnetic field as it rotates. I'm actually right on the edge there. Let's see how far that goes. You can see a lot. That's the blotch wall. Obviously, you're seeing there. The white part is where. So yeah. So that's with it under viewing film, and that we've got such a large area of flux coming out of there. Right. So wanted to show that the other day, but I forgot. So I thought, well, I'll do a live stream and show you that, so you can get a rough idea of how strong this field is on here. So anyway, I'm trying rectangular magnets. I'm not going to fit them in my device at this point. It's just something that crossed my mind, because I wound these coils a few years back, and I never really got used to it. I never got to use them really. I thought, I wonder what would happen if I put my rectangular coils in such a way, and I wanted to try the configuration. And it is interesting to see how different it performs, because my device, my generator that I built, it would accommodate rectangular coils like of this configuration. I'd have to probably trim up a millimetre on each side of the bobbins, that's all, with scissors or something. But they would fit in there. Well, anyway, it would be fiddly, but I'm focusing on I just wanted to see how it would behave with the toroid and the ball bearing, which is what I'm working out with static test at the moment. So let's, I forgot where I was now. So we were doing I don't know, did I do the current? Yes I did, because it's still on current. I must have done the current. So yeah, that was with it wired in the other way around. So put it back the other way. No, I did change it around, didn't I? I can't remember which is which then. No, I think that's right, I think. Anyway, I'll just go back on voltage. We'll soon know the voltage that we get. After all, it tends to wobble a little bit. It is balanced, but it's just it's the magnetic field that's pulling it. I'll just reset that. But there is very little cogging actually on this, because if you look, it doesn't care really where it stops. Oh, I've turned it so it's not working properly now. But it doesn't really seem to care exactly where it stops. Actually, if I took the ball bearing out, there's less cogging there, I think. I have to have the ferrite ring in there to do that, I think. Well, no worries. I've got the ferrite rings installed in these things at the moment, so yeah, because I'm going to be using these as attenuator slugs on my new build, so I've stuck them in there and I can't pull them out right now. Anyway, so I just thought I'd go over that, basically how to do static tests with these sorts of things. And yeah, you can do all sorts. You can put the coils on each side with them in series with each other, and yeah, I've tried that earlier actually, but it seemed to create more drag than anything. They seem to work best when side by side, directly over a particular pole. They do seem to work better that way, because what happens is we get this little this tilt effect as the flux is going around the coil. If it's in series, we basically get a point where the flux is strong here, but opposing down here, so it cancels itself out, and it's only when both coils are directly over do we get the maximum output, and then it kind of tilts as it's leaving on the other side, because the other pole is starting to receive the opposite pole. I mean, the other side of the coil is receiving the opposite side of the pole, which cancels out the flux on this side of the coil. So we get this seesaw effect, an alternating rocking motion of the output power, which is, a lot of people try to simulate that with electronics, but you don't really need to do that. If you just use two coils side by side, you can do the same thing. So, because both, if I take this out of here a minute, if I can move the camera, but basically you can see that this coil here is receiving more of one pole, it might be north. This coil here is receiving more of the other pole, which might be south. So in this particular position, when they're wired in a certain way, they don't produce power. They only produce power when this is over both of them like that. With it wired to that configuration, both are receiving south now, so both will produce power. So we have this locking motion in the output. So in that position, we wouldn't see anything. So it would basically turn itself off because the coil is actually acting like a switch, even though it's not a switch, because it would be receiving the other pole and the other one south, north. So, and they're in series, so it would cancel each other out, so there wouldn't be any power coming out at that point. That's why I was just testing this idea out. So I'll move my camera back, sorry about that. Right, so anyway, I wanted to explain that technique of what you can do with two coils side by side. Anyway, that's it pretty much. I just wanted to show that idea. Let's just check the current again on this. I can't remember which way. That's the ball bearing jumping up and down. Right, so that's that one, that way around. I'm not timing this at the moment, I'm just comparing. See, the current's low on, so this is with it the other way. The current's low on this side, that's where the current is pulled, output power is pulled from both the north and the south with cross series. It produces less power because it's over those points less time. Yeah, put them the other way. Much more power on that side. Right, okay, end of test. So, I was wondering if it would be worthwhile me installing some rectangular coils in my new build. Well, this is the other build I did earlier, but the new build isn't assembled yet. But yes, I will do. I mean, I'll be able to have my round coils in here, and I'll be able to use a whole slot for rectangular coils, which is the plan. So I want to compare the difference between rectangular coils and round coils at some point, and I wanted to test the theory on this jig, this static test jig, just to see if it was viable, because I certainly don't want to be putting this thing all together and building this and finding out that using rectangular coils was a bad idea, and it's not a bad idea. I do get quite a considerable amount of current out of them. Let's compare them to, can I compare them to a round coil? Actually, all my round coils were installed in this thing, and I have to slide them all out. There's a lot of farting about. Well, yeah, anyway, we'll see that we'll cross that bridge when we come to it. I mean, at some point, once I've got this and I'm measuring the RPM and everything, and I've got the rectangular coils installed and the round coils installed, I'll be able to directly compare the outputs for both sets, and that's going to be fun. Something to look forward to. So anyway, end of that test for now. I'm so glad I've still got these rectangular coils, but they're going to be a bit fiddly to fit because, as I said, they're a fraction too wide. So that means I'm going to have to I don't even know if they will fit. I might have to take a few windings off because I think there might be a few extra, too many windings on here to fit in properly. So anyway, we'll find out. I'm not worried. I don't mind taking a few windings off there. At least I'll be able to put them to use. My ball bearings escaping. Blue tack stuck at the so I actually put 310 turns of 28 SWD wire on these particular ones. I remember 3 or 4 years ago it was for the original bubbleator, you know, the one with the laminations. I can certainly still use them for this other project. I would have to just take a few turns off and trim some of the side of the bobbin off, because I'd have to fit 2 coils into each slot and they're slightly too wide. Just about, you're talking about 2 millimetres, a millimetre on each side basically. I can sort of work it out. Right. So that's where we are at the moment. Oh, I like this stand actually, I might keep it on there. It's handy, I can actually put my phone anywhere now. Yeah, I only did it so I could see it on the camera, but now I've just realised this stand is just blue tacked on the back. I can stick it anywhere. Oh, I'm going to have a job when it answers the phone though. There's some sharp metal on the back, that's the only thing. Oh well. I'll 3D print a plastic one, I think. That one will be a lot less sharp. Plus it might interfere, the metal one might interfere with the signal, I don't know yet. It doesn't seem to be, but... Right, I've got loads of these coils as well. The only problem with these is that the slots of the laminations, they're not going to be suitable for this build. That's the only thing, because I'm not using laminations, but I might actually put some laminations in there so I've still got my laminations, I can still put them in there if I need to do, and couple them to the ferrite rings at the back, so I could have the ferrite rings half and half at the back like that. I could mount the coils on the outside, that would work. I could actually have the coils mounted on the front, on the outside, coupled to the ferrite rings. That would also work, so I wouldn't have to modify them at all because there's plenty of room on the outside. I could make a new clip. I did actually make a clip that would go on the outside, so I could modify my clip so that it can accommodate 2 of these and mount them on the back end, because there's a lot more flux coming through here. And I'm not really worried about the spacing, because the flux travels down the ferrite rings anyway. Because when I take these off, like this, try and get it off without breaking anything. There you go, it's plugged in with this. Yeah, there's another ring on the back, and there's a plastic plug in the middle, and there's my toroid in the middle there, and there's my coil on the inside. It'll be easy enough to fit my coils on the back end here for doing some tests on. And we'll see how we go with that later. Put this back in there now. I don't want to break my wires off. Oh, I think I did. Did I? Where's the wire? Oh no, it's still on. It was clipping on it a bit. There we go. I like this new design. It's so much easier to fit coils and take them off and put them back in, and a lot less hassle. Yeah. Anyway, that's it for now. I was doing some more tests with this thing as well, with the put this plastic in between my toroid in the middle there. I also made it so it doesn't lift the ball bearing. Actually, I don't think this ball bearing can move now. I think I've gone close the gap too much. Never mind. Yeah, toodaloo. I'm just going to find the off button.